All right. Okay, so our second NASA Center internship talk is by Walker Nelson from St. Cloud State University. And take it away, Walker.
Oh, yes, thank you. Yeah, my name is Walker Nelson, and I'm currently a senior at St. Cloud State University. I'm working on my bachelor's degree in mechanical engineering. And for the summer of 2021, I was hired on as an intern at NASA's Glenn Research Center out of Cleveland, Ohio. The focus of my research was on the design and analysis of additively manufactured battery thermal management systems. And today I'll be talking about my research and the overall experience of working as an intern for NASA. Okay, so in this speech, I'm just going to go over a little bit of introduction and motivation for the research and for the internship. I'm going to be going over the materials, modeling, and methods for the research, go over some of the results and discuss them a bit. A brief summary and some conclusions based off of that research. And I was asked to briefly mention future work and also talk about the internship itself, working for NASA, and of course, discuss some acknowledgements there at the end. So, as with all internships for the 2021 summer, it was a completely virtual internship, and it ended up being very minimal guidelines, and it was done on purpose for the research. It was done to give lots of design space. They wanted to get plenty of new ideas from a new perspective. And it was all individual research. It was they handed me a project and I worked on it. So the internship started with a familiarization period, and that was because going in, I was completely brand new to battery thermal management systems. And again, completely on purpose, they wanted new ideas from a new perspective. And so this internship, as I previously mentioned, consisted of all individual research, where I would create new pack designs, I would test them, and then I'd bring them back to my mentors in weekly meetings. And with that being said, the internship was not without feedback. It was very well-rounded, in fact, especially as an engineering student. It followed a very structured design of coming up with a design, testing that design, and then we would bring it to the weekly meetings, and we would discuss what we liked, what we didn't like, or what should change for the upcoming weeks. So now that brings us to the topic of research, and why would NASA need to hire an intern to research battery thermal management systems? Well, with the world growing more dependent on renewable energy sources on a daily basis, batteries are becoming a more crucial part of our lives every day. And that is where battery thermal management systems come in. So battery thermal management systems are critical for batteries and infrastructure. They keep batteries operating as long as possible with maximum storage and power output. Batteries need to be kept at their ideal operating temperatures, but more than that, they need to have a minimal temperature gradient across the batteries. Now, in addition to, if you deviate the battery temperature across the battery, this is detrimental to the battery life. And in addition to all of this, proper battery thermal management prevents thermal runaway, which in the case of thermal runaway causes fire and explosions. So these packs were meant to be used in NASA's electric aircraft, the X-57, and also to be used to be rolled forward in other electric aircrafts. And as shown in the slide, it's meant to go into the wings. And this is in fact a schematic of the X-57's wing. So like I said, there were only a few requirements to keep the design space open, but there were these few. And of course, as the title says, it needed to be 3D printable. All designs needed to be additively manufacturable. As with all battery pack designs, the point is to keep the specific gravimetric energy density as high as possible. But also specific to this research, they wanted it built of 2 or more materials. They did not want a one material design. They wanted at least one to be a low density polymer. This was to keep the weight down, or also to act as an insulator in some cases. They also wanted a high conductivity material, such as a metal or ceramic, either for its thermal properties or for structural support in the designs. The final packs also had to include 12 to 16 18650 batteries, and they wanted the pack designs to minimize material volume and mass, which of course ties right back to keeping the specific gravimetric energy density as high as possible. So for this research, I decided to keep the materials constant so that way I was comparing only the designs with one another. So for the high conductivity material, I chose to use a 6063 aluminum, and that was because it had low density and high thermal conductivity. Now for my low density polymer, I chose to use TC Poly electrically insulated Ice 9 Flex. And again, it was low density, but for the polymer, I wanted a low thermal conductivity, as in the case of TC Poly. So for the methods of the testing, all of the packs were created in SolidWorks, and then they were put into COMSOL multiphysics to be tested for their thermal results. So to start off, it was decided that active air cooling was the way to go. And that was because water cooled and PCMs added too much weight to the packs. So to kick the research off, it was just some preliminary designs that were created. And in the case of this one, it was created just to test a multi-inlet design. And the reason for the multi-inlets was to decrease the dead spots that were created behind the batteries by unidirectional flow. So this pack design here is the introduction of battery sheaths. It's a little bit blurry in this picture, but I will get into detail on that in the next slide. These sheaths are just meant to act as radiators to increase the convection coming off of the batteries. And for scale reference, these inserts are just exactly as tall as an 18650 battery. So it's a 65 millimeter tall insert. The outside of the casing is made of TC Poly, and the inside is made out of 6063 aluminum. So after I had gotten started, the focus of the research switched over to looking into battery sheaths. And so the first two battery sheaths were created and tested. The first battery sheath was just a simple cylindrical sheath design, while the second one added straight vertical fins. A couple things were noticed. One, sheaths did decrease the change in temperature or decreasing the temperature gradient across the battery. However, they also added weight to every battery. So then on top of that, once you add the fins, this further adds more mass. However, it also further decreased the change in temperature across the battery. So there's a little bit of give and take with that change. So after those two were created, two more were created to test. And this left design here has more straight vertical fins than before. The previous fin design had 40 fins. This one has 100 fins. It was shown that it didn't decrease the change in temperature very much. However, it did decrease the mass, and that was helpful. Now, after that one was tested, the right design was tested, and this one has helically wrapped fins. There are 40 of them. And again, it decreased the change in temperature further. However, it also increased the mass, which is not good. So again, more give and takes to the additions and changes. So after that, those two sheaths had been tested. This left design here was the last design to get tested. And instead of having 40 helically wrapped fins, it had 80 helically wrapped fins. And surprisingly enough, this one actually came back with an increase in the change in temperature across the battery. And this was a bit peculiar, so it was actually ran 3 times. However, it came back the same every time. So after all of that, some conclusions were drawn about the sheaths, and that was that the best sheath to keep the temperature gradient the lowest was to have 40 helically wrapped fins, and that the addition of more fins did in fact not help. However, the best sheath for weight was just the simple cylindrical sheath. So after the sheaths had been tested, the focus went back to creating entire packs. And so 2 preliminary packs were created. And the top pack was just created to test the simple box pack structure, while the bottom pack was created to test the new multi-inlet pack structure. Now, the top pack is a little derivative of previous work. However, it was meant to be a comparison. Just compare the new results back to a conventional pack design. And so after looking at the bottom pack and showing what the promise of better results, it was decided that we would use this pack design for further research. And so the next step became adding fins to that pack design. And sure enough, adding those fins greatly reduced the change in temperature across the pack. And again, for scale reference, all of these inserts are 65 millimeters tall. If you were to insert an 18650 battery, it would be flush with the top and bottom. Also, for your reference, it's 114.3 millimeters wide. And again, as in the case of the sheaths, once you add all those fins, the mass of the pack did greatly increase, which is not the greatest. So that's what future improvements were designed to improve upon. So after adding fins, as I said, the goal became to drop weight. And in order to do that, the top and bottom plates were removed and were replaced with TC poly plates. Now, replacing those plates with polymer plates ended up greatly reducing the weight of the battery pack. And it ended up also increasing the electrical safety by decreasing the possibility of batteries shorting. It also increased the replaceability of the parts. So if one sheath got damaged, the entire piece did not need to get replaced. You could just simply pull out the one sheath that got damaged and reprint a new one, put it in there, and you were back on your way again. That being said, replacing the top and bottom plates did not significantly impact the temperature gradient. So in a way, it was good in that it didn't increase the change in temperature, but it didn't really help us in the change in temperature. But what we did find was a way to get it to drop weight. So after it was decided to replace the top and bottom plates, we went back to the original pack design and just started testing different spacings. Now, the reason we went back to the original pack design was in order to conserve time, because splitting off the top and bottom plates actually was very hard for ComSol multiphysics to do. So in order to speed up all the testing, we went back to a solid aluminum design with simple cylindrical sheaths. So it was shown here that the spacing within the rows was in fact way more effective at decreasing the change in temperature than row spacing. So what ended up happening was I closed the row spacing really tight. I spaced out the batteries within each row, and that greatly reduced the change in temperature in the pack. So down here, you can see that after minimizing the row spacing and maximizing the spacing within the rows, sure enough, we ended up with the lowest resulting change in temperature across the pack. So after proving that the spacing could decrease the change in temperature, it was also noted that it increased the mass of the pack as well. So again, more give and take where you may drop the change in temperature across the pack. However, you ended up adding more mass, which was not necessarily great. So once we finished with researching the spacing, we ended up finishing out the research with creating a casing, an exterior casing. And again, that was because we needed somewhere to hook the hoses up to. So it was chosen to be made out of TC poly, and that was to keep it as lightweight as possible and reduce the overall decrease in the specific gravimetric energy density. Now, for future research, more research should be done to decrease the number of air inlets, and to do this just by rerouting the air within the pack. This would conserve space and weight by reducing the number of tubes and also the amount of polymer needed to make the casing. Also, research into highly conductive polymer matrix composites can also increase the viability of the heavier options that were more effective at dissipating thermal energy. So at the end of this research, they asked me to choose what I thought was the best pack design for their application in the X57. And so I chose the lightest pack. This pack had simple cylindrical sheaths. Even though it had the highest change in temperature across the pack, it was the lightest, and so that is the reason I chose it as being the best pack. It had a pretty decent material volume, and it had actually a very high energy density, as well as high fire resistance, which is very much appreciated in aircrafts, being that it was made completely of aluminum. However, it had low swappability, so if one part got damaged, you had to replace the entire part. Also, it could use better spacing to fit into the wing better, as well as decrease the change in temperature across the pack. So now that really concludes the contents of my research, I was asked to talk a little bit about the experience itself. And so I do wish to mention that overall, NASA makes the internships very easy to be a part of. They're very accessible. Obviously, they've got their website, and you just go on there, you sign up. And it ended up being very easy. I just got a call from the mentor for the internship, and he just asked me some very simple questions, something about your school, the program that you're in, grades and GPA. And admittedly, there's a lot of paperwork when you go work for NASA, but they help you through it, and it's very easy. It's not like you're sitting there waiting through paperwork all day. They make it rather easy for you. And also, you can tell that NASA is very experienced at virtual internships. They don't make it hard at all. In fact, they send you and all your emails and your paperwork you need to fill out for your computer and whatnot. And all you got to do is you got to tell them what programs you want. You got to say, oh, I want SolidWorks or I want ComSol or whatever it is. And the other thing is, it's not the end of the world. If you forget one program, or you're halfway through the internship and you want to know more about another program, that's all good. They have an online platform where you can just go download the programs you need. So very low stress when it comes to the working environment. Also, they're very flexible on your working hours. They do require that you work 8 hours a day, but they've got a range of hours that you can work that in. So if you've got a dentist appointment or a doctor's appointment or what have you, they've got absolutely no problem. They can just reschedule your meeting or what have you. And they're all good with your schedule. Also, NASA is a very welcoming environment. You can tell all their staff is happy and thrilled to have interns helping out. And they'll help you with anything you need. If you need help with software, going in, I was completely brand new to ComSol, but they had a guy there that was an absolute ComSol guru, and he helped me right through it. He carved an hour out of his day to help me understand. And they'll also work with you on your paperwork. As I said, there's a lot of paperwork, but they'll help you right through it. They'll also help you with general understanding. You know, they get it. You're an intern. You're just getting into this, and they're more than willing to, again, carve a half an hour out of their day and help you out with your research. And so with that, I'd like to thank my mentors for the internship, Amjad Almansor, Michael Halbig, Jay Singh, and Ezra McNichols. And of course, I'd like to thank the Minnesota Space Grant Consortium for funding the research, and also thank you for the opportunity.
Any questions for Walker right now? Go ahead.
Walker, did you entertain the thought of using a Venturi effect to get the cooling effect?
I can tell you, I actually did not. In fact, I was actually at a slight disadvantage. In fact, because I'm taking my fluids class right now, actually. And so they are entertaining having me back. And actually, since I'm on a black slide, let me stop sharing. So I quit taking that out. They were entertaining the fact of having me back. And so if I could go back now that I've taken a fluids class, I think I could really apply much more fluids knowledge to the research.
Any other questions? Ben?
Yeah, it sounds like you worked with a great team. Would you maybe comment on some things you learned maybe in working with a team of people, right? As you're going through and designing these things, you're obviously getting like suggestions or feedback. What did you learn just about working as an engineer or a scientist as part of a team?
I definitely learned that, you know, you can absolutely love the design. You can pour your heart out to a design and just absolutely love it, but you got to remember at the end of the day, it's not perfect. You know, you can spend a whole week on it. So when you go to a meeting to talk to people and discuss it with your colleagues, got to have an open mind. You got to be ready for them to tell you what they don't like, because that's the only way improvements are made. For them to tell you, hey, look, I can tell you worked really hard on this, but some improvements are needed here. And sometimes that is hard to hear because you feel like you've poured everything into a design, but you got to be ready to improve.
Okay, great. Let's thank our speaker again.
Thank you.
Walker.